Hello, my name is Sam Ellicott, and I will be presenting on analog encryption for securing IoT devices. With the explosion in the number of small internet-connected devices due to the Internet of Things, there's been a growing concern over the security and privacy of these devices. It seems that every few weeks, a new exploit comes out on an internet-connected camera or another piece of consumer electronics. This has only grown more and more common as the number of these devices has increased. A key area to secure in an IoT device is its wireless communication link to and from the internet. And this has traditionally been protected by digital encryption. With digital encryption, the data must be encrypted, transmitted, and then at the receiver received and then decrypted. While this presents strong security guarantees on the protected data, it also has a high energy and latency cost to the overall system. This is unacceptable for low energy IoT applications. For this reason, we're proposing an analog encryption method, which aims to reduce both the latency and energy requirements to protect the transmitted data. In our system, we're applying a known time-varying distortion to the transmitted RF signal. Since this distortion is known, the receiver can use it to invert the distortion and correctly decode the data. However, an eavesdropping receiver doesn't know the distortion and therefore cannot correctly decode the data. This distortion can take many forms, such as a phase shift, changing in the amplitude, or a frequency shift in the RF domain. You can see an example of such a system at a high level here. We use a TRNG, or a true random number generator, to generate a phase shift on the transmitted RF signal. The value from the TRNG is digitally encrypted in the baseband and transmitted to the receiver. The receiver can use this value after it's been decrypted to undo the phase shift and correctly decode the data. An eavesdropper doesn't know what phase shift to apply to the received data because the TRNG value has been digitally encrypted. These random keys are frequently updated by the TRNG and shared with the receiver. This prevents the eavesdropper from guessing what the phase shift was. This reduces the overall energy and latency overhead of the system because the only value that needs to be digitally encrypted is the TRNG value. This value is much shorter than the overall transmitted data, and that which therefore reduces the energy and latency on the overall system. This allows us to secure data in energy-constrained IoT applications. Thank you for listening.